morning and welcome to this next lecture on complex variables. Last time we had seen the Cauchy Gorsat Theorem. We had seen this in some detail, so I will not repeat it. In brief, it says if f of z is analytic on and inside a simple closed contour named C, then integral over the closed contour f of z dz is equal to 0, the contour navigated in the positive anticlockwise direction. Okay. Now, this can be very easily extended to simply connected domains, because interiors of closed contours are involved. So, we can also say that if f of z is analytic, if f of z is analytic throughout a simply connected domain D, then integral over C, a closed contour f of z dz is 0 for every closed contour, every simple closed contour C lying in D. This is pretty straightforward extension to simply connected domains. Now, this has very important consequences. Now, consider this situation. We have a closed contour C, okay, taken in the positive sense, and suppose I have two more regions. Okay. Let us call this contour C1, call this contour C2. Okay. Let us not yet give any directions to them. Okay. So, this is the extension of Cauchy Gorsat theorem or the implications of Cauchy Gorsat theorem. So, if now I break this situation in the following way, okay, let me first say that a function f of z is now analytic on C, on C1 and C2, and in between the regions, okay, that exists between C, C1 and C2. The regions inside C1 and inside C2 are excluded. Okay. So, now I am going to apply the Cauchy Gorsat theorem here. Before that, what I do is I close these contours in the following manner. I will call this the upper part. Okay, so let me draw this again. Okay, I will call one piece the upper. Okay, this is C1 upper, C1 lower, C2 upper, C2 lower. Okay, the direction on C upper and this part is C lower. Okay, and I call this bit L1, I call this bit L2, I call this bit L3, the directions are given. Okay, I am sorry, this will be this way. Oops. Okay. So, I have two contours now. C upper comes this way, gets into L1, L1 joins C1 upper, joins L2, L2 joins C2 upper, joins L3, and then I close. Similarly, I have another closed contour with CL. So, we will see what happens now. So, I say that this function f of z, okay, with integrals C upper plus L1 plus integral C1 upper plus integral L2 plus integral C2 upper plus integral L3. Okay. This forms this closed contour. This forms this closed contour. Okay. Now, given this statement that f of z is analytic on C, on C1, on C2 and in between. Okay. So, I have the statement made for Cauchy Gorsat theorem. A function f of z is analytic on and inside a closed contour. All these little bits form this closed contour on the upper side. So, now this integral on f of z is equal to 0, f of z dz is equal to 0. Okay. So, let us see now. I have gone so far into the border. Okay. Let me just say here that is equal to 0, is equal to 0. Similarly, for the lower side, what I will do, I will take integral C lower, this one, then I have L3 but in the opposite direction. So, I will take minus L3 here, minus L3, okay. Then I take C2 lower, I take C2 lower, okay, plus integral C2 lower. Okay. Then I have L2 in the opposite direction. So, I do minus L2, L2. Then I have C1 lower plus C1 lower. then I have L1 in the opposite direction minus L1. Okay. So, this integrals, these line integrals again form an integral of f of z on a closed contour which is on the lower side. Okay. Now, the function f of z is well behaved in these regions between the circles. Okay. So, here if I have an integral going rightward and an integral going leftward, they will cancel out because the function is well behaved. Okay. So, this is also 0, f of z dz here is also equal to 0. Now, I am going to add the 2. If I add the 2, plus L3 and minus L3 cancel out, plus L2 and minus L2 cancel out, plus L2 minus L2 cancel out, similarly plus L1 minus L1 cancel out. Okay. So, what am I left with? I am left with C upper and C lower, which forms a counterclockwise contour. So, that makes it integral counterclockwise C. Okay. Then I have C upper and C1 upper and C1 lower, which is plus integral clockwise, okay, C1. Then I have plus integral C2 upper and C2 lower, which makes it again a clockwise closed contour C2. So, this set of integrals operating on f of z dz equal to 0. Okay. Now, what I will do, we need to go to the next page. I will bring C1 and C2 to the other side. So, I will have integral counterclockwise on the C f of z dz is equal to negative integral clockwise C1 f of z dz negative integral clockwise C2 f of z dz. Okay. Now, if I change the signs of this, I can change the directions of the contours. So, I change the sign and change the contour direction. Now, this is made counterclockwise C1 f of z dz plus integral counterclockwise C2 f of z dz. Okay. Now, you see the integral of f of z on the outermost contour is a sum of integrals of f of z along C1 and C2, which are contours inside. Okay. So, if I have a large number of these regions inside C, where the function interior to these contours is not analytic, but it is analytic on those contours and between the outer contour and these circles, then the integral over the outermost contour is equal to sum over the integrals of all the contours inside. Okay. Now, a further bigger consequence is, suppose there was only one. So, this is the outermost contour C traversed in the counterclockwise direction, and there was one inner contour, let us say C0. Okay. And if a function was analytic between these two contours and on the two contours, but not inside, then the integral counterclockwise on C f of z dz is equal to the integral counterclockwise C0 f of z dz. This is very big. This result is very big and very significant. What it implies is that suppose I have an integration to be done of this form on a closed contour, and perhaps the contour is somewhat inconvenient or something, then I have a singularity inside somewhere. Okay, I have a singularity. Suppose this is a situation, some contour that has an odd shape, and I have a singularity inside, and I am supposed to do the contour integral on C. Okay. What I can do is I can deform this contour into whatever convenient form I want, perhaps a nice circle, okay, and take it down as long as I do not touch the singularity. So, I can deform this contour C into C0 of any shape that I want, as long as I do not touch the singularity. So, this integral, outer integral C, the value f of z dz will be identical to integral over the convenient contour of my choice C0 f of z dz. Okay. So, we can deform the contour as long as we do not touch a singularity or cross a singularity. Okay. Now, this can be formalized, and the formal statement is there in the book by Churchill. Okay. Now, let us proceed to the next theorem. Okay. The next theorem is called Cauchy Integral Formula. Okay. Okay. In the spirit and with the pace I am going, I will give a very sketchy proof of this. The rigorous proof is there in the book by Churchill and Brown. Okay. So, I will refer to that book. So, what does this Cauchy integral formula say? Let f be analytic, f be analytic everywhere within and on a simple closed contour C taken in the positive sense, counterclockwise sense. Okay. If Z0 is any interior point to C, then twice pi I f of Z0 is equal to the integral over the closed contour taken in the positive sense f of z by z minus z0 dz. Okay. So, pictorially there is this contour C, closed contour C taken in the positive sense, okay, and there is this point z0. Okay. So, let us see how. So, as I said, I will do a not so rigorous sketchy proof. The epsilon delta type proof is there in Churchill. So, I would recommend that students look at it. So, now let me enclose this point z0 by a small circular contour and call it C0, okay, taken in the counterclockwise sense. So, now from what we have seen previously, our function f of z is analytic everywhere on C, on C0 and in the in between region. So, this particular integral f of z by z minus z0 dz counterclockwise on C is identical to the integral taken counterclockwise on C0 f of z by z minus z0 dz. Okay. Now, from the earlier portion we have seen that I can go as close as possible to the singularity as long as I do not cross it or touch it. So, here also I can go closer and closer and closer and closer to z0 as far as possible without touching z0. Okay. And since f of z is a well behaved function, f of z is a well behaved function, f of z is analytic and hence continuous, what will happen is as C0 is made smaller and smaller around z0, it will acquire a constant value of f at z0, or it will approach that value because f of z is continuous. Okay. So, on the right side I will make C0 tighter and tighter around z0, so that as f of z approaches or z approaches z0, I can put f of z 0 outside the integral. Okay. It is acquiring a constant value as I make C0 tighter. So, this is now dz over z minus z0. As I say, this is a rough proof, okay, but it is useful. Okay. So, now what I have is f of z0 and an integral over C0 dz by z minus z0. Okay. So, what is this? This is the value of the integral we began, f of z by z minus z0 dz over the original contour C, which we should not forget. We are trying to compute the value of this particular integral. Okay. So, now we have to evaluate this part, we have to evaluate that part. Okay. So, let us see what is integral over C0 dz by z minus z0. Okay. I say that we are going around a small contour around Z0, okay. Let us say over a radius r. So, my z minus Z0 I will replace with r e to the power of I theta, okay. Z then is equal to Z0 plus r e to the power of I theta, okay. Then dz is equal to, Z0 is constant, r is a constant. So, r I e to the power of I theta d theta, okay. Now, I replace everything in z with everything in theta, and so my limits on theta become 0 to 2 pi, 0 to 2 pi. Dz is r I e to the power of I theta d theta divided by z minus Z0, which is r e to the power of I theta. So, r goes out, e to the power I theta goes out, I d theta from 0 to 2 pi is I times twice pi, okay. So, if we add what is on the previous page, the integral I want counterclockwise over c, okay, f of z dz by z minus Z0 is equal to twice pi I f of Z0, okay. This is called Cauchy integral formula. Okay. Now, the Cauchy integral formula has consequences, okay. Extensions to Cauchy integral formula, okay. Now, what is the extension? So, what we say here is let f be analytical within and on a simple closed contour by the name C, and here let Z be any interior point, okay. Then we write this in a different set of variables. So, twice pi I f of z is equal to integral closed contour C f of s by s minus z ds, okay. We have written it in terms of z. Earlier we wrote it in terms of Z0, okay. Now watch what happens. What I will do is I will take this limit delta z going to 0 f of z plus delta z minus f of z divided by delta z. Okay. How do we what happens on the right hand side? Obviously I will get the limit delta z going to 0. Then I have 1 by twice pi I. Okay. Then I have the integral over the closed contour C. Okay. And here I have 1 by s minus z minus delta z minus 1 over s minus z, okay, into f of s ds divided by delta z. Okay. This is for fz plus delta z, this is for fz. Okay. So now what happens? Let me write it here, is equal to limit delta z tending to 0, 1 by twice pi I integral counterclockwise C. Okay. I do the LCM of this, okay, and what I get is f of s ds by s minus z minus delta z into s minus z. Okay. I have taken an LCM of this and brought fs ds on the top. The LCM just gives me delta z on the top, which cancels with this delta z in the denominator here. Okay. Now the point to be made here is that f of s is well behaved everywhere inside. Okay. So I can straight away take the limit delta z going to 0 in here. It is not going to cause any issues. I am not violating singularities or creating any singularities. So delta z can be straight away taken in. So what I get is 1 over twice pi I integral counterclockwise C f of s ds by s minus z whole squared, okay, and this is bound to exist. Okay, this is bound to exist. Okay. We will extend this further for a general case. So I will stop here for today. We will continue in the next class. Thank you.